Welcome everyone to the Full Spectrum series. My name is Nick Valentino. I am an assistant director in the Hajim School of Engineering and Applied Sciences at the University of Rochester, and I'll be your host for the series. This is actually the third year of the Full Spectrum series, where we invite faculty to discuss and explain their fields in an effort to inform and educate prospective and current students, parents, alums on the problems that engineers and computer scientists are trying to solve. So if you're watching this and you're interested in learning more about the problems we're trying to solve in engineering, you're in the right place. Our guest today is Dr. Marc Porosoff. Dr. Porosoff earned his PhD from Columbia University. He's an assistant director of chemical engineering and has been recently named a fellow for negative emission science. Professor Porosoff, thank you for being here. I know that between research and teaching, your plate is probably pretty full. So thank you for helping us learn more about chemical engineering.
Yeah, absolutely. Happy to be here and talk about my field a little bit and tell everybody why chemical engineering is such a great major to study.
Great. So if you could give us a little bit more of an overview of the parts of chemical engineering that you think are most valuable for someone who is looking to get into chemical engineering.
Yeah, absolutely. Can I share my screen? I can
great.
Give a little overview. All right. So can you see my screen?
Yep. Looks good.
Okay, perfect. So I'm going to talk a little bit about chemical engineering, tell you a bit about what we do in the profession. So the first thing is, what is a chemical engineer and what do they do? How do they impact our world? How do they approach problems, etc.? So I typically give this talk in person, but it's funny to give it remotely because I'll ask people, can you name one chemical engineer? And the most common answer I get is me. But myself, Marc. But one of the most famous chemical engineers is Xi Jinping, the president of the People's Republic of China. So he's a really famous one. And then another one is Dolph Lundgren, aka Ivan Drago from Rocky IV. So I'll tell you a little bit about my background and where I came from. So I've on this map kind of indicated the different places I've lived as I've gone progressed through my education. And you can see Rochester is actually the farthest west I've ever lived. So I did my bachelor's at Johns Hopkins University in chemical engineering, and then went up 95 to the University of Delaware, where I did my PhD. And my advisor actually moved during my PhD, so I followed him up to Columbia University, where I completed my degree and finished things up there. And then took a postdoc down at the Naval Research Lab, where I continued some research there after I earned my doctorate, and here I am now. Farthest west I've ever lived at University of Rochester as an assistant professor. So to tell you a little bit about chemical engineering and what we do in the discipline, it's really this idea of taking raw materials and converting them into valuable products. So if you think about chemical engineering as a whole, it's really present everywhere. If you look around the room that you're in, pretty much at every object that isn't derived from a tree or from metal is really 100% involved in chemical engineering. So anything made of plastic, parts of your computer, your laptop, your monitor, the clothes that you're wearing. So if anything that you're wearing is a synthetic fabric like polyester, that's derived from oil through a chemical engineering process. And because of this, chemical engineering is directly involved in 1/3 of global GDP. So 1 out of 3 every dollars that are created are due to a chemical engineering process. So if you really want to have an impact on our world, chemical engineering is a great major to look at. Another thing to think about with chemical engineering is chemical engineers are responsible for the Haber-Bosch process, which is how we have food. So it's how nitrogen gets converted from nitrogen in the atmosphere to nitrogen in your body. So 1/2 of every nitrogen molecule in your body likely touched an iron catalyst, which was created through a chemical engineering process that led to 2 Nobel Prizes. So sometimes there's some confusion about chemical engineering and chemistry, what the differences are. So chemists, and the big difference has to do with the scale. So chemists are more fundamental. They make new materials and compounds, and they work on a really small scale. So like vials to beakers, so like roughly the size of this coffee cup, for example. Whereas chemical engineers, we think of across many, many length scales. So we can start looking at a process on the atomic scale. So for example, how does a chemical reaction happen? How does it occur over the surface of a catalyst? But we can go much bigger, up to oil tankers, for example, to millions of barrels of oil per day converted into important industrial raw materials. So the idea for chemical engineering is we take those basic principles that chemists discover and we apply them at a much larger scale. So the COVID vaccine is a good example. So the COVID vaccine was discovered. It could be manufactured on a small scale. We could make a couple vials of it, but then chemical engineers had to come in and figure out, how do we scale this up? How do we deal with the issues of transport, thermodynamics, kinetics when we go up to a much larger scale to make enough vaccines for everybody? And so, as I said before, chemical engineering is a huge part of everyday life, and it has to do with the petrochemical industry primarily, because the petrochemical industry takes things like raw materials, crude oil, converts them into all these useful materials that we need today. But because of climate change, increasing CO2 emissions, we need to think about how to use different feedstocks. So, example, things like microalgae, plant seeds, animal fat, cellulose from waste plant matter. Apply chemical engineering core curricula to these new feedstocks to make the same things that we need to sustain modern life. And so this is a really a big interest of mine, how we can use different raw materials. And one of those that I'm very interested in is carbon dioxide directly, because carbon dioxide, as you can see in this image, is accumulating in the Earth's atmosphere. It's the dark red color in the image. So you can see CO2 is opaque to infrared radiation, which is what this image was taken with. And so we see that CO2 is accumulating in the atmosphere. And if we look forward into the future, what we can see is, based on projections, it's expected that we'll continue to use natural gas well into the 21st century. And we'll continue to use crude oil, although other renewables and cleaner fuels will increase. It's expected that natural gas and crude oil are here to stay for some time. And this is associated with increasing CO2 emissions, which is correlated with an increase in global temperatures due to the greenhouse effect. So what we're trying to think about in my group is how we get off this red line to this much unacceptable temperature rise of the Earth to get toward negative emissions eventually at some point in the 21st century. So what are we going to do to do that? Because fossil fuels are expected to continue to be around. So there's a lot of efforts that are happening to try to solve this problem. One example is in Iceland. They have all this basalt rock from volcanic activity that is naturally good at storing CO2. So they've shown, this company Climeworks has shown that they can sequester, so permanently store carbon dioxide within the basalt rock from the volcanic rock formation at about 95% efficiency. So that's one potential avenue to how we can permanently store CO2 in the Earth as limestone. Another thing that I'm looking at, it's really more of an energy storage issue, but it has to do with the Navy. So the Navy sponsors a project in my research group where they're interested in this far-out idea of taking seawater plus nuclear energy from the aircraft carriers to make jet fuel to power the onboard fighter jets. So if we think about this problem, and we think about the raw materials that exist at sea, aircraft carriers have to refuel using a refueling ship, which can create vulnerabilities to the fuel supply lines during wartime. And so if we think about seawater, CO2 is dissolved in seawater. We have water, which consists of hydrogen and oxygen. And so if we take hydrogen from splitting water and CO2 that's dissolved in the ocean, we can react them together to make hydrocarbons, really the building blocks that we need for modern life. So we can make this hydrogen renewably without emitting CO2. We can extract the CO2 from seawater, react them together through all these various reactions to make all kinds of things. And we're interested in making things like, for example, C3H6, which is propylene, produced on the order of almost 200 million tons every year from carbon dioxide and renewable hydrogen, instead of getting this from fossil fuels. And we're not as interested in making things like methane because that's already abundant and it's a powerful greenhouse gas. So we've done a lot of work in this area. We've done work on this one catalyst, molybdenum carbide, that we've come out with some publications on recently. And the idea behind this catalyst is it's not a precious metal. It doesn't have platinum. It doesn't have palladium. It doesn't have ruthenium. It's not really expensive. So it's a much lower cost, and it's active and selective because of how it can exchange oxygen with CO2. So we think about these big problems in chemical engineering. For example, I'm showing you the reaction here on the atomic scale, but we don't just want this reaction to happen on the atomic scale. We need to process gigatons of CO2. So a gigaton is a billion tons, or 1 trillion kilograms of CO2. So we want to go from the scale of just a few atoms of CO2 up to this enormous scale that could have an impact on the concentration of carbon dioxide in the atmosphere. So with that, it's a little overview of what chemical engineers do, what my group does. I have a photo of my group here, and I have several students, both grad students and undergrads, working with me on this problem. And I'd be happy to talk to you more to answer questions that you might have about chemical engineering. and my research group.
Excellent. Thank you so much. I mean, it really does put a good understanding of what the options are for students to go through and to do. I want to talk a little bit more about if you've had conversations with students who are interested in chemistry versus chemical engineering. You listed the different how they're looking at the same thing differently, but how do you persuade a student to go to chemical engineering versus chemistry?
Sure. I think that's a great question. And it probably depends on like how much of a tangible effect you want to see of your work. So what I mean is chemists are much more, I think, behind the scenes. So it's a smaller scale. So they're working on really fundamental reactions. So I've been to several PhD defenses for chemists, and their work can get like a lot more into the nitty gritty of the details of a reaction happening. And it's much more about the fundamental properties of what's happening in that reaction. Whereas chemical engineers, like if you see a chemical engineering talk, it'll be really motivated by what's the application, how does this catalyst like get implemented, how long can this catalyst work. So it's much more, you can see the direct effect on some kind of industrial process, like almost directly. The other thing is chemical engineering, generally because of that, you don't necessarily need to go to grad school, and it's among one of the highest paying jobs with a bachelor's degree.
So when you were making this decision in high school to going to college, how much was chemistry versus chemical engineering on your radar, and how were you able to make the decision? Was it before? Was it during?
Right. So I didn't really know what chemical engineering was in high school. And I think it's like a PR problem for our field because it's like a field that's everywhere. And yet I don't think many students come into undergrad knowing what chemical engineers actually do. It's like you can define it with the definition, chemical engineers engineer chemicals. Well, what does that really mean? So for me, I didn't really know what chemical engineers did, but my brother was a chemical engineer and he went to undergrad for chemical engineering. So it was on my radar in that sense. And I got to college and I knew I liked math, chemistry, science. I did well in physics in high school. I took the physics AP exam and decided to go into a major. My major, I decided, was physics. And I took physics for physicists my freshman or first year fall. And within like 2 lectures, I realized this was a big mistake because it was much too theoretical for me. So I thought, you know what, chemical engineering sounds interesting. I'll take a class in the major and see how it is. And I really liked it because you're applying physics and chemistry to real world problems. And it's so focused on solving real world problems and really understanding how the world works. And the other thing about it was it's such a valuable degree because it teaches you how to think and approach problems. So for example, with a chemical engineering background, you can go become a lawyer, you can become a doctor, you can go into academia, you can go into the pharmaceutical industry, you can go into the oil industry, you can go work for a renewable energy company. It opens plenty of doors going forward, and you don't necessarily need to go to grad school afterwards. So I don't think it narrows career options, but it makes it easier to to open your options. And that's precisely why I majored in it. I didn't know what I wanted to do. I got to senior year, I still didn't know if I wanted to go to grad school or get a job straight out of undergrad. And as such, I did a 5th year master's. So I stayed at my undergrad for another year, did some research to really get a sense of like what I liked doing a PhD. Ultimately decided I liked the academic lifestyle. I liked doing research, went on to get a PhD. And then academia was a similar decision. Like I kind of had a sense of what I would be doing in industry, but I liked the freedom of being an academic and continuing to be able to ask your own questions and investigate what you're interested in was really appealing. So I hope that answers the question.
100%, yeah. And I think one of the biggest misconceptions that students have is that this is all one plan that is laid out and will and actually, I mean, it does. It's an engineering idea, an engineering brain where like you will take these steps to get to this. So I sort of pivots towards the next question I wanted to ask you was the idea of trying to get results in research and having for extended period of time. For lack of a better word, it's you have to fail 1,000 times so you get
Uh-huh.
right one. How does that? Can you talk about your experience in research? You know, as early as you started up till now, in terms of what it is like, what sort of person should do research, what sort of person would probably gravitate more to industry.
Okay, yeah, I think that's a good question. I think it brings up like the famous, I believe, Thomas Edison quote, "I haven't failed, I've just found 1,000 ways that don't work." And that's really the way to think about research, because a failed experiment doesn't necessarily mean it's a bad experiment. I mean, there's a failed experiment because like you forgot to flip a switch when you were supposed to, or you didn't turn on the heating when you were supposed to, and that's a failed experiment. But like there's no such thing as like bad data. Like data is gonna be the way that it is for a reason or another. Like it doesn't happen randomly. And so when we approach research problems, you always want to use the basic scientific method that you probably first learned in middle school, but don't really understand, I think, until you start actually doing research and applying it yourself to a new problem. And what I mean by that is you need a hypothesis. So you need to say something, some kind of educated theory about a phenomena that might be happening. Like, for example, when we study catalysts for CO2 hydrogenation, we'll say, well, we think this catalyst might be active because CO2 really likes to stick to the surface of this catalyst. And that could be a starting point. So then we'd want to investigate, well, how well does CO2 actually stick to this catalyst? And we run an experiment, and it turns out, you know what, CO2 doesn't stick to the surface of this catalyst at all. And so then, like, maybe that catalyst doesn't work, but it causes us to think about this problem some more, and we dig deeper and we say, well, why doesn't CO2 stick to this catalyst, but it does stick to this other catalyst? And so then we start thinking about like the fundamental properties of really what's controlling this chemistry. And so if you're interested in like asking questions, I think academia and research is the right approach, because you're continuously asking questions. You ask a question, you say, well, why does this work this way? And then something happens and it leads you down a tangent, and you follow that path, continuing to ask questions about how the world works, what are the fundamental properties controlling this process. If you more so like answering questions, I think industry is the approach, because in industry, there's a bottom line. We need to make more money is really what drives the company. Like companies don't do things out of the kindness of their hearts. They do things to make more money and please the shareholders. And so like you might be working on a process in industry. Let's say you're working for a petrochemical company, and then it's all about, well, how do we switch to a cheaper feedstock? And then you try to answer this question and switch to the cheaper feedstock. You're not interested in like why this feedstock is necessarily like why does it work the way that it does, but how do we optimize our process? How do we make it cheaper? Like, let's solve that problem. Whereas in academia, it's more so let's go down the rabbit hole and figure out like really what's going on. So if I think in research you have to be really patient. So you're not going to get the results you always want. I think there's a tendency to think that like I have to oversell this and make it sound like it's the greatest thing ever and I'm going to solve the world. But like we're all working on problems that are geared toward improving humanity, and it comes one step at a time.
I have never heard it phrased as asking questions versus answering them. So I will cite you when I repeat this several hundred times, because it does put in an understanding where it does make sense, right? So answering questions in order to fix a problem, to have a customer be satisfied, so everybody can move on to the next thing. And
right.
But those in answering questions, you sometimes create the new ones, which is good.
Right.
To feed into itself.
Yeah. And just as a quick addition to that, like based on the scientific method, testing a hypothesis, what I mean by answering, we always ask questions. Like we do to some extent answer questions, but you can never prove a hypothesis. You can never state a hypothesis and say this is always fundamentally true, because there's always the opportunity you'll come in with some new theory that disproves the hypothesis, and now the theory changes. And the only exceptions are like laws. So like things like gravity, like that's not a hypothesis. That is 100% truth. Like that is a law. So that's kind of the difference, because there's always another question to ask about the hypothesis. We're an industry, like you said, it's let's answer the question, please the customer, make some money, move on to the next one.
I wanted to ask you about, because this is around the time where a lot of students are either going to or preparing to go to like conferences. Can you talk a little bit about what your experience was as an undergraduate or a graduate student and as a professional in economic conferences?
I think conferences are important in every stage of your career, but that the reason for going is different if you're, let's say, an undergrad versus a grad student versus a faculty member. So as an undergrad, I think going to a conference is important for starting to build a professional network, to get a sense of what people in your field really are doing, and to get some practice presenting, giving a poster. Like, communication skills are so paramount in any field that you need practice. You need to practice presenting. Nobody's like a natural at presenting or giving a poster or writing an abstract for a conference. That's something that comes with practice. And so if you're at all interested, whether it's industry and academia, I think going to a conference as an undergraduate is a great opportunity to talk about some work. You generally have to be involved in a research group, but like the chemical engineering department, we send something like 20, 30 students to the American Institute of Chemical Engineers conference every year. We've taken several photos. We have them on our website. So if you're doing research as an undergrad in chemistry, like the department will pay for many students to go out to ASHE. It's great. This year it's in Phoenix, Arizona. So you can get a nice break sometimes from the Rochester weather. Although last year it was in Boston, so that wasn't that wasn't much of an improvement. And then as a PhD student, it's really all about communicating your work and getting feedback on your work. So you give a talk in front of an audience who are generally experts in your field, and they'll ask you questions about what you're doing. It gives you an opportunity to kind of publicize your work and tell people about what you're doing. And then as a professor, it's kind of the same as a PhD student. It's just continuing to present your work, tell people about it, like show it to the world, because you can publish a paper, but maybe the paper doesn't get that much visibility, or maybe people want to interact with you in person, because like, as we all know, with so much Zoom, you kind of get sick of losing that element of human interaction. So like a conference, you actually get to go to the person who conducted the work and directed the research group and ask them, hey, why did you do this? Or what do you think this result means? Like, you could interpret this differently, because it's so oriented in asking questions. Like, you've opened up the doors to get more questions and dig in deeper to the problem.
So I guess transitioning to your work teaching and advising U of R, I have been continually surprised about how many students want to save the world.
Yeah.
Can you talk a little bit about what surprised you the most about UR students in your experience both teaching and advising students?
I think the undergrads here are exceptional, and I teach first years, and so first year undergraduate, first semester of college, and I teach this class, Introduction to Sustainable Energy. So we don't only talk about like wind and solar, but we talk about every type of energy technology, and we look at it through a chemical engineering lens. And in this class, it's interesting because students come in with like such a wide background of abilities, because some maybe went to like some kind of an honors high school, some maybe didn't have those same resources. So it's interesting seeing all the students come in with different backgrounds, but kind of what unites them all is, like you said, they all have this interest in sustainability and energy technologies, because they understand that energy is so important for everyday life and how we think about it, and moving to cleaner sources of fuels, for example. And so if we think about like that, so the undergrads, like I really like teaching that course, because I can see firsthand, like I'm the first one in my department that gets to interact with them. So I can see like who are the really strong students, and it impresses me year after year, because in this course, I have students write a lab report, and they write a lab report about essentially like the efficiency of heating water using solar energy. And sometimes, like often actually, students will submit lab reports that are of better quality than what I would see from PhD students and graduate students.
Oh, well.
And the undergrads here are just exceptional. So to not involve them in my research would be putting my group at a disadvantage, because we have this resource of undergrads that are available, who want to help out, who want to get involved in research, want to contribute toward these big problems, and they're here. They want to get involved, and so how could I not ask them to join my lab?
Excellent. Yeah, I mean, it is telling students while students might think that they're coming here for the open curriculum, when they're going into engineering, it's more for the research one. It's more for having access. Like you said, you're the first person they see, and you're also involved in doing all of this high level research. So it's nice to get them in that position from day one, knowing that this is what these are the opportunities you could potentially have.
Right.
As an advisor, I always like hearing other people's advice. So what type of advice would you give someone who, especially a prospective student or a current student who's interested in transitioning to chemical engineering, to do right after they watch this video? Like, what's the first step that they could do in order to think about whether this is right for them?
Yeah, I think there are a couple of things to do. I think first, you should definitely go check out our website, and we have the 4-year curriculum listed under the undergraduate pane. So you can, like, if you're in your junior, senior year, you probably already made up your mind, and it might be a little too late to switch. But if you're in your first year or your sophomore year, it's not too late to switch. There's a reason that majors are declared second semester sophomore year, because like up until then, you have time to get everything in order and catch up. So you want to sort of see where you are in terms of the courses and figure out, well, what do I need to register for next semester to get on the track of chemical engineering? And with that in line, I would also recommend that you contact our undergraduate coordinator, Jen Condit. So Jen is our undergrad coordinator. You can find her information on the Chemie website, and she is the expert at knowing how to get the courses into your schedule, how to make everything work, and she will make sure you're on track to graduate. So I think those 2 steps are really important. Then I would also recommend, like, you could come meet with me. You could email any professor in the department and get their perspective on chemical engineering and where they think you're at in chemie, and maybe approach them if you're interested in doing research too. That's something that they can help with, because as you progress in your career, you want to talk to people who have been there before and can give you advice about how you can get involved. So I help students all the time with cover letters, with resumes. Since I'm on sort of the other side, I know what companies might be looking for, how to sell yourself better, how to write a cover letter so the important information stands out. Same thing with the resume. So I'd be happy to meet, and also just general career advice if you're thinking industry or academia and you're not sure where to go. You can get different opinions from the faculty in our department.
Great. Dr. Porosoff, thank you so much for your insight and spending this time with us. I think that being able to have some of these questions answered is going to be the first step that students go in order to find out, where they want to be and what they're going to do.
Mm-hmm. Great.
So the full spectrum series will return with other areas such as biomedical engineering, optics, computer science, and much more. So please feel free to share this video. Dr. Porosoff, again, thank you so much for being here. I mean, this was really provide a lot of clarity, and it will be definitely beneficial.
Yeah, great. Thank you so much for having me.
All right. On behalf of the Hajim School, thank you for watching, and we hope to see you soon.